Hello and welcome to G Fun Facts Online. Imagine being able to hear the voices of our ancestors from thousands of years ago, not just their stories passed down, but their actual words, their poems, their everyday chats. For centuries, countless languages have gone silent, their wisdom seemingly lost forever. But what if that wasn't the end of their story? Today, we're diving into the incredible world of computational archaeolinguistics, a field where artificial intelligence is literally resurrecting lost languages, giving us a direct line to our distant past. This isn't science fiction. It's a new frontier of science where archaeology, genetics, and AI are teaming up to decode humanity's forgotten voices. So how does a language die? And how have we tried to recover them before AI? For generations, historical linguists have worked like detectives, painstakingly comparing related languages to piece together their common ancestors, what we call proto-languages. This is known as the comparative method. It's brilliant, but it's also incredibly slow and laborious, limited by the sheer complexity of the data. At the same time, archaeologists were digging up the physical world of these lost cultures, pottery, tools, buildings, giving us a tangible, but silent, picture of their lives. The two fields, linguistics and archaeology, ran on parallel tracks, one studying the intangible word, the other the tangible object. Then came the digital revolution. Computers gave archaeologists powerful new tools for mapping sites and analyzing artifacts. This became computational archaeology. Meanwhile, linguists got a massive boost from natural language processing, or NLP, the same AI that lets computers understand human language. The real magic happened when these two worlds collided. Researchers realized they could combine all this data, the where and when from archaeology, and the what and how from linguistics, and feed it into powerful algorithms. But there was a third, game-changing piece of the puzzle: genetics. The study of ancient DNA, called archaeogenetics, allows scientists to trace human migrations and relationships with incredible precision. This is the principle of triangulation, combining evidence from archaeology, linguistics, and genetics. If the spread of a language family matches the spread of a particular farming technique and a specific genetic lineage, you have an incredibly strong case for how a group of people and their language moved across the world. For example, the farming/language dispersal hypothesis suggests that major language families spread with the expansion of agriculture. And now, with genetics, we can see the DNA of those farmers spreading across continents alongside their linguistic legacy. This brings us to the engine at the heart of this revolution, the AI itself. How does a machine learn to speak the past? One of the most important techniques is borrowed from evolutionary biology, called the phylogenetic method. Just like biologists create a tree of life using DNA, linguists can use word lists and grammar rules to build a family tree of languages. These algorithms compare thousands of features across hundreds of languages to figure out the most likely branching pattern, showing how, say, Spanish, French, and Italian all diverged from a common ancestor, Proto-Romance. But it gets even better. By adding geographic data, these models can pinpoint the likely homeland of a proto-language and map its expansion across the landscape. This is how researchers are testing big theories, like the idea that the Indo-European languages, the family that includes English, Hindi, and Russian, spread from the Eurasian steppe thousands of years ago. But what about analyzing the texts themselves, especially when they're written in forgotten scripts on broken tablets? This is where natural language processing, or NLP, gets a serious workout. Ancient texts are a nightmare for computers. They're often damaged, with no spaces between words and inconsistent spelling. But specialized AI models are being trained to overcome this. They can perform optical character recognition on ancient scripts, essentially learning to read them. They can also automatically identify cognates, words in different languages that share a common origin, like the English, one, and the Latin, unus. This is a cornerstone of historical linguistics, and I can now do in seconds what used to take human experts months. The most cutting-edge tools, however, come from the world of machine translation. The same technology that powers Google Translate is being used to decipher ancient languages. These are called neural machine translation models. Early versions used an encoder-decoder system. The encoder would read a sentence and squish it into a numerical representation, a thought vector, and the decoder would then use that vector to write the sentence in a new language. A major breakthrough was the attention mechanism, which let the decoder focus on the most relevant parts of the original sentence as it translated, which is crucial when languages have different word orders. Today, the state-of-the-art is the transformer architecture, which relies entirely on attention and can process massive amounts of data with incredible efficiency. For ancient languages where we have very little text, researchers use a technique called transfer learning. They train a model on a big language like English, and then fine-tune it on the small dataset of the ancient language. The model transfers its general knowledge of how language works, giving it a huge head start. This all sounds amazing in theory, but let's look at some real-world case studies where this technology is making history. One of the most stunning successes was the automated decipherment of Ugaritic. This is an ancient Semitic language that was actually solved by humans back in the 20th century, which made it the perfect test case. Researchers at MIT built an AI system that was given Ugaritic text without being told anything about it. By using its knowledge of how languages tend to change over time, for instance, a P sound is more likely to become a B than a K. The AI correctly figured out that Ugaritic was related to Hebrew and successfully translated many of its words. That same system was then used to challenge a long-held theory that the ancient Iberian language was an ancestor of modern Basque. The AI found no link, supporting what many modern linguists had come to believe. Let's talk about a big one, Proto-Indo-European, or PIE. This is the hypothesized ancestor of hundreds of languages spoken by billions of people today. Using computational methods, researchers created a database of grammatical features from 125 different Indo-European languages, both ancient and modern. By applying phylogenetic models, they were able to reconstruct the most likely grammar of PIE, spoken around 7,000 years ago. Their findings confirmed what linguists had long suspected. PIE was an incredibly complex language, with intricate systems of grammar similar to ancient Sanskrit or classical Greek. And the ambition is growing. Researchers are now automating the entire pipeline. One project took data from over 600 modern Austronesian languages, a family spoken across Southeast Asia and the Pacific, and used probabilistic models to automatically reconstruct their proto-languages. The results were astonishingly accurate, matching over 85% of the reconstructions done by human experts. Another team did the same for Proto-Romance, the ancestor of French and Spanish, automatically generating a proto-word list from 50 modern Romance languages and dialects. The machines are not just helping, they are starting to do the heavy lifting of reconstruction themselves. Of course, this incredible power comes with huge responsibilities and challenges. The biggest practical hurdle is the scarcity of data. Deep learning models are data hungry, and for many ancient languages, all we have are a few fragmented inscriptions. I can't just invent information that isn't there. This leads to a second danger: misinterpretation. Reconstructing words is one thing, but understanding a culture is another. We risk projecting our modern biases onto the past. A reconstructed word for leader might mean king, priest, or temporary war chief. The context, which comes from archaeology and careful human analysis, is everything. This raises an even deeper ethical question, sometimes called digital colonialism. When a lost language belongs to a marginalized or indigenous community, who has the right to revive it? Well-intentioned researchers could impose their own interpretations without the consent or participation of the descendant communities. It is absolutely crucial that this work is done in collaboration with these communities, prioritizing their knowledge and their wishes for their own heritage. And finally, it's vital to remember that AI is a tool, not an oracle. It cannot replace the deep contextual knowledge and interpretive skills of human linguists and archaeologists. The best results come from a partnership between the computational power of the machine and the critical thinking of the human expert. So what does the future hold? The field is just getting started. As AI models become even more powerful and specifically designed for fragmented data, we can expect even bigger breakthroughs. The great unsolved mysteries of linguistics, like the undeciphered scripts of the Indus Valley Civilization or the proto-Elamite script from ancient Iran, may finally be within our reach. By analyzing more and more reconstructed languages, we can ask fundamental questions about how language itself evolves. Are there universal laws of language change? What drives it? But perhaps the most profound impact is a personal one. To hear the resurrected words of our ancestors, to read their thoughts from millennia ago, forges a powerful connection to our shared human story. The whispers from the past are growing louder, and thanks to artificial intelligence, we are finally learning how to listen. Thanks for tuning in to G Fun Facts Online.